the system. So multiple responses will form a spectrum. So and then like we discussed before, okay, we need to see the fundamentals of the response spectrum, how it is comprised, why code adopt the response spectrum method, why code develop the elastic curve for the response spectrum, and then why we are required to follow that. So in today's session, we will do just like two fundamental topics, and we will not go in too much details, just the fundamentals. That's it. Just to get the feel and sensing of it, right? Okay, why it is, and then why code adapted this way, why code did not adapt in the other way, right? Okay, exactly what we are doing now these days. So the like in the previous sessions we discussed that okay, if we try to understand in a very simpler model. So this is just basics, very basics you did in your high school, ninth and 10th grade, junior or senior years, or most probably the freshman years, right? And then you see the time required to complete one cycle is the time period, and then time period you are seeing it as soon as the stiffness of the structure is increasing, the time period is decreasing, mass is increasing, the period is increasing. Okay, and then this is the simple displacement versus time chart. Like I said several times, I always use this word because I have done some heavy utility projects and some complex projects. I have seen the most critical and the most important and the most challenging work in any structure is to set the period, to kind of like balance the period. Period is if your period is good, remember, okay, memorize this kind of like this sentence or a statement. If the period is good of your structure, I mean the period of the vibration of the structure, right? If the period is good in both directions, then your structural response will be will be predictable. Okay, you will see the response of the structure in a predictable manner. If the period has a problem, seriously, so then it means that the kind of structure you are designing or constructing, probably it would not give the same response as you are planning to do it or as you are intending to do it. So this is simple harmonic motion. The system would like to repeat it back and forth. So this is simple. You have been doing it for a longer period of time, so there is no need to explain too much. You have already done it. We have done it in our sessions too, and then you have seen it so many times before. This is once again the same kind of like a wave form, but just wanted to make sure you understand the concept of damping. The damping is a magic word. No one understands 100% what damping is, right? But in order just to understand, we say if there is zero damping, the system will never come to the equilibrium system. System will keep oscillating, keep oscillating, and it is infinite kind of oscillation for the same system, right? If the system has any kind of damping, what is the meaning of damping? Simple words, it is the friction within the system, okay, which brings the system back to its equilibrium, or which brings the system back to its what do you say, zero state or zero stage or zero phase. So that's we call, you know what, because of damping it has come to the zero state. So as you can see, the wave is going, you can see the amplitude, you can see how it is decaying, and then finally it becomes zero. But the other system, there are two systems. One system has the damping zero, the other system has the damp, and there is some 5% damping. So the system which has the damping, it comes to zero. The system which is undamped, it is not coming to zero. Okay, so now let's move to the next slide, which is once again very simple and straightforward. Okay, if we have the function as the applied force, so see, harmonic loading near the natural frequency causes magnified response. Code already captures it. We just in few moments we're gonna study this. Okay, what exactly I'm trying to say. The resonance is a serious problem, but the problem is okay, when the earthquake comes, the structure will only respond to that frequency which matches the structure will resonate on that frequency which matches the frequency of the wave from the earthquake. Okay, we know the resonant meaning What is the meaning of resonance? It's going to increase the amplitude, and it is a problem. But if you follow the response spectrum elastic curve, so it is already considered, it is already, the response has already been kept. If I put very careful words, I would say the response has already been captured in those uh, in between those contours, the contours which we discussed last time, how the elastic curve is developed. So in that way, you can say that yes, if we follow the elastic curve from the ASCE response spectrum curve, so we are good with that. Okay, but remember that there are some critical concepts. So T is equal to 2 pi root m over k. The mass is directly proportional to the period, and stiffness of the system is inversely proportional to T. Right. Second concept. See, these are the just fundamentals. What is important about, if you are in my companionship, if you are in my friendship, so I always say to you, try to understand the meaning of the words, try to understand the concept and philosophy of the words, right? So next concept is damping. Third concept is resonance, as you can see over the screen. And now look at this is very important, multi-harmonic responses. Okay, what is this? So you can see, once again, see the period, and here is the response. Response can be anything. Response can be velocity, response can be displacement, response can be um, multiple variables which are associated with the system, multiple physical variables which are associated with the system, but specifically under the consideration. Okay, what I am targeting, what I'm trying to see, so that's called the response of the system. So if you see, this is wave one, wave two, wave three, and look at the response of this. Once again, independent variable on the horizontal axis, dependent variable on the vertical axis. Once again, it is period. I have been keep saying to you, period, period, again period. Your period has to be right. Once you will start doing some kind of like critical structures, like refineries, like manufacturing industries, like power plants or high-rise structures, even mid-rise structures, period becomes a serious problem. So you have to have the feel and the sense of the period. If your period is coming right, then it means everything most probably inshallah will be right. So let's try to understand what is the meaning of multi-harmonic responses. High responses resonance one, at resonance with wave one. So you see the spike, there is a significant spike. Why this spike is coming? Because of the resonance. That's it. That's the only reason. And here, the other reason is because most probably the system frequency matches the frequency of the excitation. Whoever is exciting the system has the same frequency as the system has inherent natural frequency. So that's why we are seeing the big spike, and then we are seeing the decay, then further decay, then further decay, and then it dies out. And this is the input motion for the system, right? So an earthquake. So I put like few points which I really want to highlight on the slide which we are discussing. Okay, an earthquake contains a mixture of many frequencies. See, when earthquake comes, like we discussed before, in the nature, everything is kind of like mixed. It's not like you will never see the straight line, but it's hard to find it, right? Everything is some kind of like, it's a mix of like difficult, simple, moderate difficulty, and then everything is mixed. Complexity, less complex system, soft system, hard system, semi-rigid, semi-soft system, or semi-hard system, some kind of things. Everything is mixed in the nature. So an earthquake contains a mixture of many frequencies: high frequency, low frequency, medium frequency, and these are the frequency ranges, right? But the building does not respond equally to all of them. Building does not respond because right now you are sitting where you are sitting right now, on your desk, on your floor, on in your bed, or whatever, wherever, on even on your table, there is earthquake is going on. But see, is your building responding to that earthquake? No, it's not, right? So because the frequency is so low, you are not even feeling it. So but the building does not respond equally to all of them. It responds strongly only to the frequencies that match its own natural modes. Okay, What is mode? We discussed the last time that this is the specific pattern of displacement, the vector displacement, and it has the specific frequency, it has a specific mass participation. That's called the mode, right? So it's mode of vibration. That's called the mode of the vibration. Okay. And what graphs is telling us, okay, earthquake motion contains many frequencies. You see wave 1, wave 2, wave 3, each frequency excites different modes, meaning, well, see, if you have one system, let's say if you have some kind of cantilever, some kind of system, right? So you have lumped mass here. This is M, and you excite the system with the external function, meaning you provided the ground, you did the ground acceleration, you accelerated the ground with some kind of like there is some frequency in that wave, right? So each frequency excites different modes. So, and if you have one more mass here, so you see here, okay, this system gonna move like this way, right? So most probably this is the mode, this is first mode, this is the shape is the first mode shape, right? So but is it like always? No, it can move like this way too, right? It can move like there will be multiple modes. It depends on the how many modes we are excited, how many modes are being excited within the system due to the externally applied function or externally applied force, right? It makes sense to you guys, right? And then the strongest response happens when a wave frequency is equal to the building mode. Let's say the structure is responding, the structural, the whatever the structure is there, it has some kind of natural frequency inherent. That frequency has been hit by the external applied frequency, then a structure going to respond to that frequency, right? And that will be a resonant frequency as well. So the response spectrum is the envelope of all these responses. This explains why response spectrum analysis works, because it captures, see, it captures all the responses, and you got the peak right here. This is the actually, when I will design the system, I will take this max value is my design value for whatever the system I'm designing. See, that's why it says the response, it does not say anything else, just the response. A building vibrates strongly only at periods where the earthquake contains significant energy. These periods appear as peaks in the response spectrum. So these are the peaks. Okay. Next mode. This is you got to this is the question I was just asking to Samir. Okay, what is the first mode? What is the second mode? What is the third mode? I have okay, guys, pay attention what exactly it is. This is your lumped mass, right? Mass here, mass here, mass here means meaning three floors. So first mode, displacement due to mode 1 at floor 1, displacement due to mode 1 at floor 2, displacement due to mode 1 at floor 3. If I displace the system, if I apply the force at this system or excite the system, what's going to happen? It's going to vibrate, it's going to oscillate from its point of equilibrium, and the first shape, something like this, we are getting this is called the linear shape, right? The linear mode. Look at here on the response spectrum where this mode is. This is way far, meaning the period is somehow larger than the other points, right? So the period on the graph is, or period on the x-axis, which is the independent axis, and acceleration is the dependent axis, vertical axis. So you see that this period is far larger than the period of the second and third mode. But is it the only shape which is in which is this the only the displacement curve, displacement vector, sorry, the right word is displacement vector in which the system gonna respond? No, system can do this way too, system can do this, something like this, right? So all these modes, what happens when you excite the system will go in all the modes, whatever the modes are excited by the external function, by the external force, right? Whatever the force you apply, system will start oscillating, then it will exhibit some kind of like simple harmonic, is for us to understand, we call it simple harmonic motion. And then we are saying the first mode system going to move like this way, second mode, this is the displacement vector, and the second mode system going to move like this way, and the third, the system going to move like this. So this is just for our understanding how the system going to move, right? But how, where all these modes gonna fall on our response spectrum curve? first mode far away from the second and third mode. So in theoretically speaking, so this is the largest kind of like period, right? Because it is taking larger time, longer, not the larger time, longer time to complete its one cycle. So that's the first mode. And typically, most of the responses, the longest period is the first mode, where we capture the highest amount of effective mass participation, and also the system exhibits the longest period. So what does it mean? It is going to be the fundamental mode of vibration, right? That's why we call it the fundamental mode of vibration. But is it like true the entire response can be captured in first mode? Possible, most of the response, but the second and third, then it will have some impact, because maybe we will get the response here like 90%, then 5%, 7%, 3% right here. But is the system is responding only in this mode? Yes, as a major portion, system is responding to our excitation for the first mode, but its system is also experiencing the second mode and the third mode. As you can see over here, displacement curve are showing okay, the system is actually the lumped masses at each floor, they are oscillating and being displaced from its neutral position. So then what we can do, we can combine all the model responses, either CQC method, complete quadratic method, or square root of sum of the squares method, and then combine all of them, and then get the one response. If we combine all of them and get the one response, then we can use this curve, and then we can design our structure, right? So but remember that this shape is very critical for you. And now see the next important concept you got to understand: shear mode. What is this force? If I apply this force here, if I apply the force here, if I apply the force here, obviously the mass going to move like this way. That's why this mode is called shear mode. What is this? This mode is called shear mode. And this mode, the definition of the shear mode is that this is the deformation dominant mode. This is the deformation dominant mode, right? So usually the first mode in which the system is see the linear displacement, this is the displacement curve, this is called the shear mode. And the system is showing the displacement, and we are saying okay, this is because this is coming from the shear deformation, so we say because it is producing the shear deformation, that's why the name of the mode is shear mode. Maybe this mode will come in the second or third, maybe possible. Most of the time, more than 90% of the time, every structure, whether it is pendulum type of structure or any other structure, first mode is something like this right here. So usually we fall fundamental mode of the vibration usually is the shear mode. Okay, makes sense. And then what happens when the lateral force displacement relationship becomes non-linear? Because the story shear resistance has reached yield strength. If you come here, you see the design acceleration is right here, but we force the system. I told you, okay, if we divide with the r in the what do you call it, with the for the base shear, so then we kind of like forcing the system to yield. It should go some kind of deformation, right? Why? Because we want to have some kind of ductility in the system. We want to dissipate the earthquake induced energy by displacing the system. That's the only reason, right? We cannot design the system at this level right here. We have to divide it by a strength reduction factor, because we want some kind of like inelasticity in our system. That's why I see this word inelastic response spectrum. That's why this is called inelastic response spectrum. Theoretically this is what it says, right? But in reality we are talking everything within the linear stages, meaning within the elastic stages. And then what happens when the something fails into the shear mode? Shear mode, which one is the mode? This one is the shear mode. Remember that this is the shear mode. And what happens in the shear mode? This can happen due to plastic hinges in the beam or column. Let's say you have a system, right? And then you excited the system somehow from here, you keep increasing the force, probably the hinge will form here, right? So you will clearly see. I'll share in next few after after a few sessions, I will start sharing with you some of the earthquake projects we worked, and the projects, some of the projects, they have experienced the earthquake, and then we got the opportunity to see exactly what happens to our shear wall, what happens to our bracing, what happens to our movement frame. So you're gonna see, clear short distortion right here. So it means that the hinge has formed over here, right? So this shear mode comes plastic hinges in beams and columns, yielding in braces. So if I have, let's say, if I have the brace here, forget about this hinge. So obviously this gonna fail first. So it will, I either I will have hinge here, or something somewhere this path, because my brace got to fail. Cracking, crushing in shear walls, sliding, rocking, coupling beams yielding, shear of flexure yielding involves pierce yielding. What is the meaning of yielding? Yielding, when the system starts yielding, meaning the inelasticity is coming into the system, because there is significant drop in the stiffness in the system. Okay, there is a significant drop in the stiffness of the frame. So then we see, then what happens, system goes into the elongation of the period, right? Then it goes into the phase of the elongation of the period. So if yielding starts in your system, so then what happens, the stiffness drops, period increases, inelastic spectrum applies. So meaning you are somewhere in this range. Okay, flexure mode. What is the flexure mode? Why this is called the flexure mode right here. Second mode and third mode is the flexure mode. Why? It is kind of a curved. That's why they call it the flexure mode. So if someone asks you, okay, which one is the shear mode? So this is the shear mode. So you're gonna respond, oh no, this one is the shear mode. Someone maybe ask you, okay, what is the period coming? What is the frequency coming in your shear mode? So you will calculate in ETAPS or SAP or whatever. You're gonna say, okay, this is the, when you get this shape, so this is the shear mode. When you get this shape, this is the flexure mode. So in flexure mode, what happens? So flexure modes, if the response on a curve, then it's the flexure mode, right? So what it says right here, so these modes look like curved shapes, similar to a bending column or bending beam, right? So, but see, pay attention. Even in the shear mode, the fundamental mode of vibration, the period is the longest right here. And if it for the flexure mode, the fundamental mode of vibration is right here. But do we consider just one mode or two mode? No, we combine all the modes for our spectrum. Make sense what I'm saying? So shear mode shape, floors move sideways like a stack for the shear mode. For flexure mode shape, structure curved similar to a bending beam. Okay, same building, both exist. For one structure, shear mode exists, and one building, the flexure mode exists. Okay, when the structure yield shear mode, stiffness drops sharply, period increases a lot. Flexure modes, stiffness drops less, period shifts gradually. There is a big difference. When you're going to do the modal analysis in the ETAPS, you're going to see, pay attention on the results, right? When you do it like one of the projects where, this is how I start reading it. Which mode the structure is going actually. Stiffness dropping sharply, period increases a lot. Mode 1, mode 2, mode 3. And then flexure modes, stiffness drops less. If stiffness is dropping, but less, not as compared to the shear mode, right? But and period is here, period is increasing. Here, period is shifting, changing, but gradually, not a sudden or not an abrupt change. Okay. So far what we discussed the harmonic motion, we discussed the damping, we discussed the resonance, we discussed the multi-harmonic response of a system. Then we discussed the response spectrum comprised of the different modes of vibration. Then we discussed the fundamental mode. What is the fundamental mode of the vibration? What is the definition of the fundamental mode of the vibration, which has the longest period, and most probably it's going to have the highest amount of effective mass participation, meaning when you excite the system, so this is where the mass is participating Okay, where is the, this is at this point where the mass is participating, at this mode where the mass is participating. So that's called the effective mass participation. Okay, so these are very critical. All of them are fundamental but critical concepts in order to develop the base, in order to lay down the foundation for the response spectrum analysis. Okay, so then we discuss share mode. What is a share mode? This mode is a share mode. This mode is the flexure mode, and why it happens, and then what kind of yielding or cracking you will see in your system. Now the next slide, elastic response spectrum. See this spectrum, you please again, like I discussed the last time, I spent significant amount of time. And why we are spending significant amount of time? Because in the for the rest of your life, this is kind of curve you will be dealing for forever, because you will always develop, even for the site specific spectra, you're going to develop something like this. Or if you're following the code, or even now these days for all the modern codes, they are not going with the peak ground acceleration, they are going with the spectral acceleration, right? And this is where the main difference comes from the UBC and IBC. That was the primary reason to move forward from UBC to the IBC, because UBC goes with the peak ground acceleration, but that's not the reality. That is important, because if there is an acceleration, then the structure going to feel some acceleration, right? But the, we discussed this spectral acceleration. We spent significant amount of time on it. Why? Because the entire concept of the seismic analysis and the response spectrum curve in IBC in IBC, which refers to ACE. AAC primarily is primarily dependent and completely dependent on this concept. It's spectral acceleration. What it says how much effective acceleration is coming into your system. Make sense what I'm saying? How much effective acceleration is coming into your system, right? See, I this is the ground. If I have a building and then it is not attached, it is just sitting right here. So let's say this is just, you just put it over here, and I excite the system. There is some ground acceleration, PGA, peak ground acceleration, right? So they actually, if it is not attached, so whatever the acceleration is, it doesn't matter to me, right? So the damage or the hazard or the risk, all philosophies will be completely different, because it is sitting, it is just sitting right there, like a book is sitting on a table and then you are moving the table. That's called peak ground acceleration. Simple concept, right? And this is what the UBC targeted, but IBC did not. The AEC didn't. The IBC did not target that. IBC target, no. Okay, if you attach this, so there is peak ground acceleration, but what is the effective acceleration felt by the system which is attached with the ground? So once you're gonna excite here, there you have some excitation. So this system, whatever the object is right there, whatever the building structure, it's gonna feel some kind of acceleration. This is not going to be the same acceleration right here. No, because this acceleration depends on so many variables. The most important critical variables: mass, stiffness, damping. Okay, these three will decide what will be the acceleration of, what will be the period of this is what will be the acceleration, and ultimately what will be the period of the system. That's called the spectral acceleration. What the system felt, what the system actually felt. This is the definition. If it is attached, then it is called spectral acceleration. Otherwise, there is no spectral acceleration. If there is a book sitting on your on the top of your table, it's not. You start shaking your table, book gonna feel. Of course, book is moving, right? And it's gonna see some kind of acceleration. It's gonna see some kind of displacement, but that's not spectral. It will become spectral when whatever the in reality is it is feeling. Okay, when it is attached with the system. Okay, and then how it would respond. So it would the response of the system will be dependent on mass, stiffness, and damping. These are the most critical parameters. So this is the most fundamental spectral acceleration curve. You will always keep seeing it, keep seeing it, keep seeing it. Here is the maximum acceleration you can see, and then this decay, it's gonna start decaying, and then you will go into the constant acceleration zone, and then your period will become large and large and large, right? And ACE7, we discussed this in too much detail. If I remember, I discussed the first where it is. We discuss the constant acceleration, then we discuss the constant velocity, then we discuss the constant displacement region. So there were like four region probably, and then we discuss in detail, okay, how, and then which equations control the region, the response of the response of the system, and then which region controls which equation controls which region. So these are all coming from the code. Okay, so but remember that this is the extremely important. That's why Pfizer sent you the Excel sheet. You need to understand, is it the true curved line here? Yes or no? But first we need to understand what it is. Then we will go into the background of this line, right? So if you see, okay, you have, this is the constant acceleration, and then you have the constant velocity, and then you have the constant displacement. These are the three critical concepts you got to understand. You need to understand what is the short period, what is the long period, and why. See, this is 1 second, why this is 1 second, and why it is here 2.2 second. So this all these numbers are extremely critical and extremely important to understand the philosophy behind the response spectrum curve given in the ACE 722 or ACE 716 or 710 or 702 or 705. Okay, IBC 2000 introduces the response spectrum curve concept with the spectral accelerations. But I really want to go before going into because we already discussed this, but today we're going to discuss the next step. In order to discuss the next step, I want to touch upon something different. This is important, and at the end of the sessions, Faiza will go through the Excel sheet, and then you will understand. I just want to explain the super critical concept. Please pay full attention. Please pay full attention. Eat it, drink it, dream it, digest it, memorize it like you memorize the Bible. Okay? All right. Pay attention. On the on horizontal axis, we have the period in seconds, right? Whatever you can change the units. On this vertical axis, you have the spectral displacement. Excuse me. Spectral. Now the word spectral, you understand. If I say the spectral displacement, if I say spectral velocity, if I say spectral acceleration, you understand exactly what we are trying to say over there. Why we are not saying just the displacement. It's spectral displacement, meaning the system, stiffness, mass, damping, everything is coming into the picture in the response of the system. And here we have spectral acceleration, which is acceleration due to, it is measured in the same unit as in terms of the acceleration due to gravity. Pay attention what I'm saying, because last time Noor asked a very good question. Sir, this is actually the acceleration is changing, and then at that time I just said, okay, because we did not discuss this, so I said last time, okay, you know what, this is the constant velocity region, just assume it. But but pay attention what's happening when you excite the system. Okay, whatever the system and whatever is happening, when you excite the system, you see okay, there is, of course, it's gonna move back and forth. You take the spectral displacements, you plot this curve. What is the spectral displacement curve? Spectral displacement curve is this. Okay, this is going all the way. You see how it is going, a big hump, and then kind of this is the constant velocity region. This is the and this region is different. Please stay with me, because you got to understand. You need to understand from where the response spectrum curve in the code is coming from. Okay, and then this region will become the constant displacement region. And now see, spectral displacement, from spectral displacement, what I try to get from the spectral displacement to the spectral acceleration, because the problem is we cannot get the spectral acceleration directly from the observation. We need to have first the displacement, then from the displacement we get the spectral acceleration, and that spectral acceleration, so there are so uneven spikes and stuff like that. So code introduces very important concept. Pay attention. Pseudo spectral acceleration. What the word I used? Pseudo spectral acceleration. So this is fictitious and this is real. But when you see the response spectrum, you always see something like this. You're gonna say, sir, what? Okay, are we designing something fictitious based on the fictitious graph? Yes, that is true. Because the spectrum we use in IBC is actually the pseudo spectrum, is not the real spectrum. This is the real spectrum. And why I'm saying that this is a real spectrum, I don't know if this is, there is, oh no, hold on. You see, this is the displacement history. This is actually been recorded with the real earthquake record, which I sent to you, Altadena. I think something, there was some name. You guys, I'm gonna give you the. We're gonna start doing the all the files which I sent to you. You will develop, or you will share with all the time versus displacement charts, right? So you see, this is the actual, but this graph is coming from the actual seismic record, actual seismic record. But are we designing for this? No, this is, we are not, like, we are taking the actual, we are calculating the spectral display. Listen to me very carefully. Spectral displacement. From spectral displacement, we get the spectral acceleration, and then final thing which we actually use in the code, or which we develop, is the pseudo spectral acceleration. What is the pseudo meaning? If you are in, if I ask you this question, what do you understand the pseudo acceleration, or pseudo velocity? What is the meaning of pseudo velocity? Or, oh, let's put like easy, take it easy. What is the meaning of pseudo force? See, if you are in like if you're in, like, in any elevator, lift, right? We call it elevator over here, right? So if you are in elevator and you are going up, your mass, let's say your mass is like 90 60 kilo, but you're gonna feel 75 kilo when you are going up with high, with the higher amount of accelerations, right? So what is this force called? Is it the real force? No, this is the fictitious force. This force is something, there is a name for this force. Same way, when you are in the lift or the elevator, you are going down, you feel weightlessness. Your mass is actually 70, let's say like 50 kg, right? But you are feeling -5 or -10 kg. You are feeling weightlessness. What is this force called? So this is something fictitious. So this is actually the concept of pseudo force comes from there. It is the fictitious, but it is very critical concept. Why? Because this is because this pseudo acceleration, this is actually the code is using it, and there are reasons for the code to use it, right? So what is the meaning of pseudo acceleration? So this is not the real acceleration, but why we are using it. So we get from the actual seismic record the spectral displacement. We develop spectral acceleration is right here. You see this is spectral acceleration, and then we develop the pseudo spectral. This curve, this the red curve, is called the pseudo. But you can see right here, you will say, oh wow, my acceleration is this, but I am going somewhere here. What's going on? Yes, this is what the decision by the court. But because the court decided, okay, no, we cannot follow the exact and accurate accelerations which we record, which we get the record from the site, because we need to capture why they did this, why they introduced the pseudo spectrum curve, or we call it in the common language, we call it elastic response spectrum curve in ASC. But it is, in reality, it is the pseudo curve. Okay, this curve is something like this. Like here, see this red line is pseudo. Pseudo means it's fictitious, in unreal. But what it is something like this. So constant acceleration, then it's coming right here, and then it's dropping, dropping like this. Is it not? See, is it not the response spectrum curve in the code? Yes. But is it the real curve? No, it's not. It's a pseudo curve. It is the pseudo spectral acceleration curve. But why code did this? Because code, like I told you before several times, the code kind of like took like 1,000 earthquake records, then selected 100, then from the 100, then take the most representative earthquake records, then develop this curve, then they come up with this technique. You know what, we got to go pseudo curve. Why we got to go pseudo curve? Because they checked okay, most of the more than 90% of the structures on the planet, they respond somewhere here in this, from here in under this curve, this pseudo curve. This is the pseudo curve. See, you will not find this the word pseudo curve in the code, but you will find somewhere in commentary, but not in the main body of the code. So in main body of the code, you will always see, oh, it's spectral acceleration curve or elastic response spectrum. See what I'm writing here, response spectrum curve, right? Because this is the most common line. But from where this curve is coming, that's the most critical concept. That is coming from the actual spectral displacement. Then you get your and from that spectral displacement you develop all this, you develop these two curves, spectral displacement, and then you get the spectral acceleration, and this pseudo curve is formulated from there. Does it make sense what I said? It makes perfect sense. You are getting actually, and why code did this, the pseudo philosophy, code went for the pseudo philosophy just because of one reason, because they wanted to capture they wanted to capture the response of the structure within this spectrum. That's the only reason. Because if they go the actual earthquake record, it's not possible. If code go, because code has to generalize. You understand my point? Code has to generalize something for everyone, right? So what code did? Code took all the records, developed these three graphs, and then decided to go with the response spectrum curve like this, because the all more than 90% of the structures will definitely come in under this curve. That's it. Will definitely fall under this curve. And then they decided to go, you know what, this is the design curve we're gonna follow in the code. Make sense what I said? Is this is see, this is maybe some words I used, maybe not 100% accurately describing the situation, but I tried to convince the concept. See, the response spectrum curve you use is the pseudo curve, it's not the actual curve. And it is coming from multiple variables behind the scene, and it is coming from the 100 earthquake records. But those 100 earthquake records uh, had been selected or were selected from thousand and thousand earthquake records. You understand my point? And this is the time history, and the time history of your displacement versus time. And see the spike, and then going all the way here, and then it's coming down and it's becoming zero because of the damping. So this is very you got to I would say you need to memorize this, eat it, whatever. How this is response spectrum curve is coming, what is the constant acceleration zone, and why this constant acceleration zone, and what is the constant velocity zone, and why this constant velocity zone is coming. Actually, everything is coming from the pseudo curve, right? So this is like kind of like very very critical and very very important. Now let's move to the next topic. No, it's not the next topic, same thing again. We have been discussing this curve for past like 2-3 sessions. You remember code says 0.2 second, right? This is very important. And then code says 0.1 second. What does it mean? And this is the short period, this is the long period. What does it mean? Okay. And so 0.2 something over here, right? And one is something over here. Okay. So where this peak is, okay, this is one. So you can see 1 and 0.2. Why? What you can ask the question, okay, my friend, why code choose to just two bounds, upper bound and lower bound? What is the reason? 0.2 and 1. Code should have used 0.5 also, 0.675 also, zero point 0.9 also, 0.75 also, 0.55 also, right? Why specific to 0.2 second and 1 second? There is a big reason for it. Because at 0.2 second, what happens? We get the highest elastic base share of the system, highest elastic base share of the structure. 0.2 second highest, because this is here is the maximum spectral acceleration on the pseudo curve actually, but what we call it elastic response spectrum curve, right? And why 1 second? Because on 1 second, this is the we got, so zero point 0.2 seconds we got the peak acceleration, and also what we get, highest elastic base share of the structure. And 1 second we get the peak drift and displacement. On 1 second, we get the peak drift and displacement, meaning maximum flexibility demand or peak velocity response. Okay, so that's why, so these 2 points lets the code control both force and drift behavior. Make sense? And why again? Why point two and one? Because with all those iterations, observations, and experiments, what they found out, because this, see, the research is continuous, right? They found out that no, they are not capturing the response of any general structure from, they are not capturing the 100% response. These are zero point 0.2 second and 1 second. 90% of the structures on this planet always falls between these two contours, always falls between these two control points. And why? Because code is doing it, because code want to enforce some kind of restrictions for to control force on your structure and to control the drift on your structure. So this 1 second period is actually drift control period, right? Because, man, pay full attention. Why this is 0.2 second and 1 second? And this is seriously, this is very critical. If 1 second is actually to control the drift of your system, the drift of your structure, and 0.2 second meaning to control the base shear of the system. So you will see, most of you have been doing the seismic analysis for a longer period of time, have done many high rises, mid rises, and many critical structures, but they need to understand exactly what is the meaning of this curve and from where this curve is coming, and what is the meaning of 0.2 second, what is the meaning of 1 second. 0.2 second, you understand what is the meaning of 0.2 second? Meaning is simple, 5 hertz, 5 cycles per second. And if you see here, where is the, yes, right here. Okay, first wave of earthquake for 0.2 second and 1 second period. See, 0.2 second, I just included over here, just undamped, and I really just see, this is not the ideal, or this is not the practical wave shape right here, practical waveform right here, but it is just to get you feel. What I always say, you must start feeling the response. You must start feeling, you must start sensing the response, because there are people who just see the building. You are the one who feel the emotions of the building. Okay, na? You are the one who feels the emotions of the structure. Point to look at the amplitude. Look at 5 hertz. Wow. So this is 5 hertz. You are analyzing the structure for your 5 hertz. Obviously, this is going to control the base shear, right? And look at the 1 second. So 5 hertz, what does it mean? Very fast shaking, snappy acceleration pulses, short wavelength energy, dominates base shear. What I said to you, dominates the base shear, anchorage forces, and diaphragm shears, right? We'll definitely will study how to calculate all these forces, but first we need to understand the fundamental concepts. Why code chooses 0.2 second? That's the question you got to ask yourself in your dream, while you are sitting, while you are eating, while you are driving, while you are traveling. You got to ask your question. You got to ask this question to yourself. Why 0.2 second? And then look at 1 hertz, 5 hertz, 1 hertz. It's slow, it's smooth. Drift control, what I said, drift control governs drift, affects mid-rise and high-rise buildings. So one hertz wave is like this. 5 hertz wave is it's very fast, super fast, right? If let's see, at the end of the session, if I can play a video, then you will see if I made a video with a seismic isolator, 5 hertz, how the vibration looks like, and for 1 hertz, how the vibration looks like. Okay, come here. Summary of IBC spectrum, 0.2 second, fast, sharp, high acceleration governs base shear. Amazing concept. And the 1 hertz controls the drift. Make sense? And why it is happening? Earthquake ground motion contains a broad range of frequencies. Make sense what I'm saying? Earthquake ground motion contains a broad range of frequencies, but most of the damaging energy falls between 0.2 second and 1 second. What they noticed, what IBC noticed, they noticed that most of the damaging energy from the earthquake on our structure falls between two frequencies. Those two frequencies are 0.2 second. Those two frequencies are 5 hertz and 1 hertz. Make sense? 5 hertz and 1 hertz. Isn't it amazing? Okay, those are the two frequencies where 90% of the structures on this planet will see the most of the damaging, most of the damages. Make sense? Because you can come back, you can say, oh, I'm doing one time history analysis. This is a spectrum, but my spectrum is going outside of the, let's say, like 3 second, 4 second, 5 second. What's going on? So I am again and again using 90% or more, 90% or more. 90% or more structures will experience the most damaging energy for the waves is between zero point 0.2 second to zero point 0.2 second period to 1 second period. Now you got the answer. Okay, why the response spectrum chose 0.2 second and 1 second period? Why the response spectrum chose the 5 hertz and 1 hertz frequencies? Because the earthquake, the earthquake ground motion contains there are so many broad ranges, right, of the earthquake frequencies, but these two are the critical. That's why we chose it. For 0.5 second we did not see that kind of damages, general damages across the structures. We see maybe in about 20% structures, but 90% of the structures will experience, 90% of the structures on this planet will experience the damages between the bandwidth of these two frequencies, like 5 hertz to 1 hertz. Make sense? This slide is very critical to understand the concept. But this is the ideal, because system is doing this, and then coming to zero because of the damping. There is zero damping right now. It is just to give you the feel. Your heart and your mind should start like sensing it, should start like feeling it, right? Makes sense what I'm trying to say? And you can see, okay, how why the 0.2 second and then 1 second is so critical, why the constant acceleration zone is critical, why the constant velocity zone is critical, why the constant displacement zone is critical. You can see it. Okay, and then this is, but see, most of the structures we design like 2 seconds, 3 seconds, that's it. Very rarely you design the structures for 20 seconds, like Verrazano Bridge in New York, which connects the borough of Staten Island to the, I think, Staten Island to the other borough is Brooklyn. No, not Brooklyn. But that was the like longest suspension bridge. It has the period 20 seconds. So what kind of structures has the higher period? We discussed this before. Either it has a seismic isolator at the base, or it has the these are the suspension bridges or something like this. That's why code introduced the concept of 4 seconds to 16 seconds, if you remember that, right? So because there are tall buildings, there are high-rise structures which are actually being constructed with the seismic isolators, so they can displace as much as they can go under the controlled displacement, right? They can have the tune mass damper, they can have the damper at the top like Petronas Tower, right, in Asia. So it means you can have the higher response, you can have the higher period but controlled drift. Okay, so that's why AAC, you remember you were asked, we were discussing 4 seconds to the 16 seconds. So those were for the high-rise structure, which has either the damper at the top, or the seismic isolator at the base, or the suspension bridges like Verrazano bridges. The Verrazano bridge kind of like 20 seconds. My professor was saying it's equal, close to the 20 second, because he worked on that project. But anyway, so let's move forward, and then we discuss this time history. And the next concept, before we go to the next concept, I really want to go back, and again I would like to repeat it. Harmonic motion, simple, you understand. System would like to repeat it. Okay, once being excited, system would like to, once you touch it, okay, once you touch it, it would like to start repeating itself. Okay, if zero damping, it will go forever, it will go on and on forever, right? Never gonna come back. Damping, then we discuss resonance. Then we discuss multi-harmonic responses. We discuss how the spectrum captures the multi-harmonic responses from the different waves at the resonance level, right? Then we discuss what the same structure gonna see like multi-modes, right? Where those modes gonna lie on my response spectrum curve. Now you understand why I'm saying, okay, just right now understand the concept of the curve. This curve is actually pseudo curve. It's not the real curve, right? So now we try to understand the shear modes. Then we try to discuss the flexural modes, right? The curve modes, shear modes. Usually, the where is the shear modes will look like something like the displacement vector will be like this, and these are the flexure modes, the second and third modes, right? And the fundamental mode of vibration we said, okay, where we will have the longest period will be the longest period mode is the fundamental mode of the vibration. Okay, then we discuss, and this is what we discussed the last time in very much detail. Okay, this is the constant acceleration zone on the response elastic response spectrum curve. Then we have then we have the constant velocity transition. Why we are calling it constant velocity transition? Because from this curve, because of from this curve we are calling it. Okay, now you understand constant velocity transition period. Then and this after this period, TL, so these were like T naught, T sub naught, T sub S, T sub L. So this is the constant displacement transition period. Okay, now you kind of like have the full idea that this response spectrum shows the full energy level of the system, how it is responding, how it is responding against the external excitation, which is nothing except the energy, right? This is also the form of energy, right? You are seeing right now at the moment. Okay, and so this will conclude our response spectrum understanding from the AC7 or IBC. Okay. If you guys have any questions, you can ask Faisal. Now you can close. What do you call it? You can close your video. Okay. Okay. Okay, guys. Now I would like to request is any of you.